Hello everyone, this is Parth this side. Today I'll be explaining how deep salt algorithm works, and this is my assignment for the BA lab. I have made a PPT for this, and let's start by explaining it with the PPT. You know. So we'll be understanding heap sort algorithm. It is an efficient sorting technique. The introduction for heap sort can be considered as it is a comparison-based sorting technique based on binary heap data structure. We all know what a binary tree or a binary heap is. It sorts an array by building a max heap or a mini. We can also make a main heap here and repeatedly extracting the maximum element. What we do in this algorithm is we extract the maximum, or we can say the root element of any binary heap data, and we put it into the sorted array. I'll explain through the visual representation of the algorithm. A binary tree is a binary heap is a complete binary tree where the value at each node is greater than or equal to its children. So, the upper part or the greater one is usually known as the parent, and the lower one is usually known as children. We sort takes advantage of max heap property to efficiently sort an array. This particular algorithm can be explained by visually more rather than verbally. The steps on heap sort algorithm. It's to build a max heap from the input data. First of all, we have to build a max heap from the input data, and obviously, as I told before, we extract the minimum or the maximum element from the root of the heap. Place it at the end of the array. Now, I'm using maximum element here for avoiding the confusion, and I'll be explaining through maximum element or max heap technique. But we can also use the minimum heap technique here. We'll reduce the heap size and heapify the root element to restore the max heap property. Now, the property of max heap is that the root or the parent element will always be greater than the children element. This is the property of max heap, and we'll use this particular property for sorting an array. Let me show you. Okay. So here we have an array here. It's 4, 3, 7, 1, 8, 5. First of all, we made a binary tree of this element. We took the first element, which is 4, and then we put its children, which is 3 and 7. Then again, we have the children for 3, which are 1 and 8. Then we have 5 as as child of 7. But this is not, maxi. We converted this into maxi. As I told, the property of maxi is that the parent element should always be greater than the children of child element. First of all, we'll not touch the leaf or the bottom elements of this tree. What we'll look at, the non children, or you can say the non leaf element of this tree. What we are doing here is comparing three with its children. Again, no, one is obviously smaller than three, and eight here is larger than three. So what we did here was we swapped eight with three, okay, and then we also compare the four, and it's the we'll start from the lower part of the binary tree, obviously. What we did was we compared 7 and 4, and again 7 is greater, so we swapped it. Then again we have a you know comparison 7 and 8, so we swapped it as we know. Now here we have a maxi. Here we have a maxi, or we can just it's easy to understand. Maxi is basically easy to understand. What we did was we swapped 3 from 8 because 8 is greater. Then we swapped 8 from 4 because 8 is greater, obviously. Yeah. In any case, the time complexity of maxi and mini both are same, so it doesn't matter. We'll have a sorted array in the same time. Okay. Now here is what exactly a heaping file, or you can say heap sort algorithm does. We have a max heap here. Its initial elements are this is we have a max. We or we take the root of this max heap, which is like the topmost part, and we put it into the sorted array, and we replace it with the bottom right, the element which is in the rightest bottom rightest part. Will replace it with the root. Okay, so we took 8 here, and we put 8 into the sorted array, and obviously we replace 5 with 8. Now what this is what a heap sort algorithm does. But again, we have a binary tree here, but it does not have property of max heap. What as I told, the property of max heap is always that the parent element should always be larger than the children element. Okay, so what we did here was we put 5, uh, the topmost. Okay, sorry, we have a max heap here. We have 7, the topmost. Okay. We put 7 into the sorted array and we replace it with 3, which is the bottom rightest element of the binary. Now again, we have a new binary tree, but again, this is not a max heap. Why? Because again, the parent element should be larger than the children element. Okay. Again, 5 is obviously larger than 3, which is the parent element. So we'll replace 5 with 3 because obviously the parent element should be larger than the children element, child element. Now we again have a proper max heap here. We'll again do what a heap sort algorithm does. We take the 5 off and put it into the sorted array and replace it with the bottom rightest element. Uh, Obviously, we replaced it with 1 because it is in the bottom rightest part of the heap. Again, we have a binary tree, a small binary tree, but it is not a heap. Why? Because again, the same concept. The parent should always be greater than the child. So we made max heap out of it. What we did was we replaced 4 and 1. Again, part to be noticed is that both of the children are greater than the parent here. But which one is greater? Which one is more greater? So 4 is more greater than 3 when compared to 1. So 4 is becomes the parent here. Again, we do the same thing. We put 4 into the sorted array and we replace it with 3. Okay, now again, we have a what we can say particularly binary tree. It's not that much of a big binary tree. Again, we'll do the same thing here. It is already a maxi. As you can see, it is already a maxi because the parent element is larger than the children element. So we did again the same thing. We sorted what this algorithm does. We put 3 into the sorting array and replaced it with 1. Again, at the last, we have only 1 left and we put it into the array. Now here we have a sorted array, which is 1, 3, 4, 5, 7, 8. But if we have before 4, 3, 7, 1, 8, 5, which was the unsorted one, we have a 1, 3, 4, 5, 7, 8, the sorted array. This is how basically our heap sort algorithm works. There we go. Uh, I explained this example. Okay, this is another example of just heap sort algorithm. Now, what is the time complexity of this algorithm? The best case was O n log n. We have the following: first and the average case. The space complexity is O1. This heap sorts in place. The efficient advantages of heap sort. Advantage basically include it's efficient, time complexity in all cases, efficient, and log n time complexity in all cases. In place sorting requires only one constant amount of additional storage. It takes, only one constant amount of additional storage while executing. It is very, very preferable or suitable for large data sets in which, much sort of big sort can't be helpful. Uh, while having this, I'll quickly share you the code for this, heap sort of. Uh, we have used Python in this case. So what we did was we use the function CP. So this is visible. Yes. We use the function heapify, initiate the largest as the root, no, then the left as the child, right child, the as extended before. If, if the child is larger than root, we'll replace it, and if the right child is larger than largest so far, it will replace it. Uh, there we go. We have used, okay, we have used Python here, and particularly we have an example. The array is 12, 11, 13, 5, 6, and 7. This is the array we have now. If you use this, we will get the array 5, 6, 7, 1, 11, 10, 11, 12, and 13. This is how in code or in the compiler how this happens. Coming back to the PPT, these are the example that we saw, and that is all we have for the heap sort. Again, I would like to mention this. We can also use minimum heap and we can also use maximum heap. In both of the cases, we have the same type of complexity. That's all I would like to say.